Okay, so we're going to now talk about the speed of the shock. So what we've got is we've got an abrupt change in the density. So that's the density here, rho, as a function of x. So there's an abrupt change in the density. Now, what happens is the cars are arriving at a certain rate here and are leaving at a certain rate here, and it's going to make the shock move up and down in time, just from conservation of cars will give us the speed of the shock. So and obviously it doesn't have to be a straight line, it can be, it can be wobbling or doing anything, but it's whereas you've got this abrupt jump in density as the shock. The conservation of cars is going to give us the speed of the shock. So we've got a flux of cars coming in here. Cars are arriving at a certain rate and they're leaving at a certain rate. And if the cars are accumulating, like at a traffic light, it'll move backwards. If the traffic lights turn green, it'll move forwards. So you've basically got a quantity here, which will say, the rho plus, and a quantity here, which is rho minus. And then you've also got a quantity here, which is the flux, the positive flux, and the negative flux. You can imagine here that there's going to be some way of writing down an equation. You can just use kind of common sense. So the about how this would how the shock would move, but we're going to derive it formally. We do it as follows. We take some point. So the shock here, this is the position of the shock is S of t. So we have conservation of cars. So we say d by dt, this is the first, same as the equation we wrote at the start, but because there's an abrupt jump, we have to be really careful in taking the derivative inside. S of t plus, this is funny notation maybe, but it's just the integral from x1. So here's, let me change colour here. This is some point x1, and this is some point down here, x2, where the shock jumps. We're jumping across the shock, and we're going to take the density dx is equal to, and we've got this flux, right? Q minus Q plus, a flux. Okay, now when we do this derivative, we pick up a term here, s dashed of t times rho of, and because this is the density below, we get rho minus. So we get the s dt times rho minus the s dt times rho plus from here, plus we get the integral from x1 to x2. We can take the density inside here, there's time derivative inside. X equals Q minus Q plus. Okay, so of course this becomes, changing colour again, this thing here becomes equal to 0 as x1 goes to x2. So we just squeeze in around the shock, and we rearrange this equation, and we get ds dt is equal to Q minus Q plus, difference in the jump and difference in the flux divided by the jump and difference in the density. Okay, it makes perfect sense. So basically, if there's more cars arriving than leaving, then it moves one way, and etc., etc. Okay, so here's a picture of an example here where the shock forms. It forms 1 second later or something. You can see the first point they cross. So they've got this hyperbolic tangent, and you can see here what happens. And this is perfectly in balance, so it just stops here at 0, and the thing overturns. Another way to track the shock is just to equal areas rule. It's the same formula. This area here must equal this area here. So you draw the line down the middle as it twists over. But there's the shock forming, and it's just this abrupt jump in density from 0 to fully dense. it's kept in equilibrium because less and less cars are arriving and these cars are slowly driving away, well, it's just enough sort of creeping away to keep it in balance. But that's the problem there with the shock. So the last problem we're going to do is this Riemann problem here. So it's exactly like the problem we have with the expansion fan, except it's the same rho L when x is less than 0 and rho R when x is greater than 0. But this time rho R is greater than rho L. Okay, so what happens here? Basically, we've got a shock forms, and we've got to follow the shock. So there's an abrupt jump, and that abrupt jump is going to move. Nothing more than that's going to happen. So what we've got to do, if we look at the picture here, and this will help us out, we've got one set of characteristics coming out here, going this way, and we've got another set of characteristics in another colour coming out this way. Whoops. Okay, and they meet immediately. And then what we want to do, the shock, is this middle part here, the happy medium. The shock is in the middle of these two curves. Halfway between them is the shock. So I've kind of drawn one a little bit too similarly, so it almost looks like it's straight up, but that's the shock there. So that's S of t. Okay? So basically, rho of x comma t is going to be equal to rho L if x is greater than the shock position, if x is less than the shock, and rho R if x is greater than the shock. So we've got to work out where the shock is, and it's the average of these two slopes. So this is x equals c of rho RT, and this is x equals c of rho LT. So we've got to take the average of those 2 points. And there we go. So this is going to be x equals 1/2 c of rho LT plus c of rho RT. Simple as that. That's the position of this magenta shock. So the shock is equal to 1/2 the average of these two. Or we can write it as T over 2 times C of rho L plus C of rho R. Okay, and we can use our formula for what C of rho, so it's very difficult to see which is the bracket and which is the C. That's supposed to be a letter C and that's supposed to be a bracket. But the formula is written down on these notes here very clearly, and I'll just show us that. There it is there. And there's a picture here of this, exactly what I drew. There's the characteristics crossing, there's the middle line, and there's the solution, the shock. In this case is the moving forward. And you can see here the twisting solution gives you these two areas. This blue line is the twisting if we follow the characteristics, and we equal areas and moves forward like that. Alright, I finished traffic waves, which I'm very happy about. Hopefully this recording is perfect.